All clear?
Okay, welcome everybody to today's INQA online seminar. It's the 5th of November, and this week's speaker, I'm very pleased to have Steve Campbell from University College Dublin and the Free University in Berlin, who's going to be talking to us about speeding up quantum annealing with engineered dephasing. So over to you, Steve.
Yes, thank you very much, Paul, and thanks very much for the invite. So, yeah, it's a pleasure to be able to talk to the community. As I was just saying to Paul there, like this is my first foray really into the world of studying quantum annealing. So the focus of what we were trying to discuss here was trying to overcome what I think is one of the kind of core bottlenecks in most of these annealing protocols, which is that generally you need to do the protocol relatively slowly. Like one of the kind of core aspects is that you have this slow ramp that you need to do. And my background in quantum control techniques is trying to find ways in which we can speed up that process whilst not sacrificing the efficacy of it, right? While still being able to achieve the same target that you would. So what we kind of came up with was studying like your basic annealing problem and to see, is there a way in which we can manipulate the dynamics, and in particular, can we do something like engineer some sort of coupling with an additional external environment that allows us to speed up the annealing part of the process without necessarily sacrificing anything. So I just quickly thank my collaborator. So really, Mikolas was the kind of leader who did basically all of the sort of nitty gritty work on this, and then Josias, Raphael, Christiana, and and also Giovanna Marigi as well involved. So let me just jump in. This first slide is completely superfluous, I think, for this community, for this audience. But let me just humor me for a second, just to get everyone on the same page. My understanding of what the kind of key problem that we want to do with quantum annealing is, we have some problem that we can define in let's say generally some sort of optimization problem. We want to find some extremization of some function. This can be mapped. Smart people have figured out how you can map this to effectively something like this like an easing problem. So you can take some complex optimization problem, you can map it to an equally complex problem. But the benefit here is that this allows us to encode the solution of our problem. So instead of extremizing this function, we can map the problem to what effectively looks like a easing, a sort of various dimensional easing chain, something like a classical easing chain, where the ground state of this encodes what our solution is. Right. So I imagine everyone watching this fully aware of this. The problem is that while this problem encodes the ground state of this Hamiltonian encodes our problem solution, finding that ground state is obviously difficult. So the idea, I think, or the whole motivation of quantum annealing is, okay, I know what these coupling terms are. I don't know what the ground state of this Hamiltonian is. I can exploit the inherent rules of quantum mechanics in order to do this by, instead of achieving this Hamiltonian in the first instance, I prepare my computational register, let's say my collection of qubits, in a much easier to prepare state. In particular, I just apply some sort of strong polarization to it. So everyone points up in one direction. This comparatively super easy for me to do. And then I can just use the basic rules of the adiabatic theorem that if I ramp the system sufficiently slowly, I can just turn off the strong polarization I have while slowly turning on the problem Hamiltonian. And if I do that sufficiently slowly, then I'll be able to maintain my system in its ground state, and then I can read off what my solution is, right? This is the basic point. So lots of work done on formalizing this idea and doing all the quantum annealing. What this talk is about, and really what my focus is on this bottleneck, is this adiabatic evolution. Because what the adiabatic theorem tells us is that in order for this to be achieved, in order to do this ramp slowly, well, I need a notion of what slow enough is. And in particular, the adiabatic theorem tells me that the spectral properties of this Hamiltonian that I'm trying to implement, that's what dictates what we mean by slow. And because I don't actually know what the spectral, I know some details about the spectrum of this Hamiltonian, right? I know these coupling terms, but I don't actually know fine spectral details. So in particular, I don't know what that lowest ground state energy gap is between the ground state and the excited state, which is what dictates whether or not I can even do this evolution sufficiently slowly. So the question is, can we cook up a scheme which allows us to implement this adiabatic evolution, but on, in principle, slightly faster timescales? So let us quickly just recap what our basic textbook quantum mechanics tells us about what we define by adiabaticity. So for quantum systems, adiabaticity essentially can be paraphrased as just going super slow, right? So what the problem we want to do here is we want our problem Hamiltonian to be realized by tuning from this easy to prepare, highly polarized state and slowly turning on this interaction term while slowly switching off this polarization field. So adiabatic theorem basically says that if the rate at which I'm ramping the system is sufficiently slowly, then I can I can achieve this dynamics perfectly. What we mean by sufficiently slowly is that the rate at which the Hamiltonian is ramped should be sort of inversely proportional to what the energy gap is. So if I have a very, very, very small energy gap, I need to go extremely slowly. And that's kind of the core bottleneck here. So we think of what the main option and how to achieve this is. The obvious thing in general is go slowly. But this is not an optimal approach, right? Because the problem there is if we are ramping the system really slowly, then it leaves the let's say whatever I'm doing my computation on open to other potential spoiling effects, right? So it'll be the system will be susceptible to noise because the thing takes so long. The other, and I think the more fundamental bottleneck here is that because this problem Hamiltonian, like the whole point is that we're looking to find the ground state of it. And while like I said, we have some notion of what the spectral range is, like we know what these coupling terms are that when we've mapped our problem to this easing problem, we don't actually know the fine spectral details. And what the adiabatic theorem needs is for us to know what the energy gap is between the ground state and the first excited state, let's say. That's at least the minimum amount of information we would need in order to define a meaningful notion of slow enough. Without that information, we have no idea what slow enough even means. So adiabatic dynamics kind of from the textbook is not particularly useful to us when implementing something like these annealing protocols, I think. So where I come in or where our interest is, well, me and Christiana and the guys have done a lot of work on quantum control. And so the natural question is, well, can we do it by speeding up this process using something like some advanced control techniques? And the first thing that like for at least for me would think about is something like what's called a shortcut to adiabaticity. So this is a technique that uses the bare Hamiltonian, the original Hamiltonian that we have, something like this H of t, and figures out a way essentially to achieve an effective adiabatic dynamics, but on a much shorter time scale, right? And we don't need to know too much about the details. Sufficient to say that if I know what this Hamiltonian is, I can work out what kind of control terms I need to add in order to speed up the dynamics. Similar kind of things go for other control techniques like optimal control and other approaches one can take. But what's common to many of these is that they kind of either implicitly or explicitly assume you know some detail, like quite a bit of spectral information about the Hamiltonian, which again kind of renders them sort of not very effective when it comes to something like a quantum annealing protocol, because again, the whole point is we're trying to find the ground state of this problem Hamiltonian. We necessarily do not know fine spectral details. So we want to see, is there a way in which we can achieve an effective shortcut adiabaticity, like speed up this adiabatic dynamics, while not needing to have any particularly fine-grained details about the spectral features of my original problem Hamiltonian. That's kind of the whole thing that we're doing. And our answer kind of comes from environment engineering. So the idea is, well, one thing that I know I can't fully protect the system from the surrounding environment. Maybe I have some tunability at the level of the environment, or maybe I can couple my problem Hamiltonian to something which acts a bit like an environment, and maybe there I can speed up this dynamics. I can achieve this effective adiabatic dynamics while without needing to know any particularly fine-grained details about the problem Hamiltonian beyond just what its inherent coupling terms are. So this is kind of our motivation. We want to look at this environment engineering approach. And where we took inspiration from was really some work that Christiana and Giovanna, Josias and Raphael had been doing before, where they were looking at a very similar problem to see whether or not they could speed up the dynamics of something like a single qubit. And the framework that they were thinking about was, well, it's kind of there was a kind of intuitive idea that we can see. If I think about what happens in doing some sort of adiabatic, or let's say some sort of finite time dynamics, I have a Hamiltonian, like exactly the problem that we have in our quantum annealing protocol. I have some Hamiltonian that I'm ramping time dependently. If I do it too quickly, what will happen is if I've initialized everything in its initial ground state, I do a finite time ramp. What ends up happening is whatever the spectral gaps are, finite time ramps will lead to some excitations, which manifests as coherences in the energy eigenbasis. So the rationale is if I can suppress coherences in the energy eigenbasis, in particular, if I can induce strong dephasing between the energy eigenstates, then I should be able to achieve an effective adiabatic dynamics essentially by just ramping up this dephasing strength. This is like the essence of what these quantum non-demolition measurements do. And in fact, this is the kind of picture that we had in mind. We said, okay, let's take our problem Hamiltonian that we want to achieve this adiabatic dynamics for, and we're going to couple it to what we call a meter. This is the sort of standard nomenclature in these QND type settings. We want this meter to interact with my full problem Hamiltonian in such a way that it essentially induces a dephasing, that it suppresses any coherences being built up in the energy eigenbasis, and that should be enough to essentially affect an adiabatic dynamics. And then we want to see what sort of level of control do we have if we tune up the essentially something like the interaction strength here. So if we look at what our general Hamiltonian for this non-demolition setting looks like, it's something like this, right? So we have what our problem Hamiltonian is, which is our time dependence. We're then going to couple it to this meter using some interaction term. And then we have the free evolution term of the Hamiltonian. What this does, right? It's not an easy to, it's by no means, we'll talk a little bit about the physicality of how you would implement this control term later. It's not the easiest thing to implement, obviously. What we have here is a time-dependent interaction term, time-dependent at the level of what the bare energy of the problem Hamiltonian is. But we just want to demonstrate the proof of principle idea that this type of interaction gives rise to this effective dephasing mechanism. And to see, does that allow us to speed up our adiabatic process in particular? And can it be applied to something like an annealing protocol where we have comparatively little information about the specific structure of this, or let's say of the spectral properties of this Hamiltonian? So a few little caveats here. One is that we assume that the Hamiltonian of the meter commutes with the system Hamiltonian. That's sufficient to ensure that really it is just a dephasing interaction, that there's no energy exchange between the two of them. But we will see that we can relax that constraint later on. So kind of main point that I want to get across, or what's nice about this setting is that we can understand the effect of it in a very, very like an oversimplified setting. So what we look at in the first instance is my favorite world, which is just that of a two-level system, right? So it's not really a practical problem, but we just want to demonstrate the essence of what this kind of quantum non-demolition type approach implements. And we'll see that all of the qualitative features that we see here in this simple two-level setting ports over directly to the let's say proper annealing protocol when we have a proper problem Hamiltonian in place. So what we just few details here, but like what we look at is this famous Landau-Zener model, where what the question or what we're targeting to do is we're going to start with the qubit essentially initialized in something like it's a strongly polarized state, and then we're going to ramp through until it's polarized in basically the other direction, right? So we just choose some parameters such that that's essentially what this protocol will do. So we parameterize it in this way, and this is a very famous problem that was, and I think you look at the early papers, Landau and Zener solved basically this linear, this problem back in the 30s. And what we know is, like, if you look at the spectrum of this simple two-level system, it has an avoided crossing, right? So we have that there's a big energy gap initially. As we ramp that, the time parameter, as we ramp through to get through to the other side, we go through this sort of minimum energy gap in the middle, right? So this G sets what our minimal energy gap is. What the adiabatic theorem tells us is that if this ramp, this linear ramp is too fast, we'll end up getting excitations. We'll end up leaving the ground state and we'll get some excitations into the excited state. What we want to see is using this coupling to the meter, this quantum non-demolition inspired approach, can we speed up that same dynamics relatively simply, right? And the answer is obviously yes, right? So what we look at here, so we just look at, for just this simple single qubit case, this boundary here at x0 equal to 0, this is essentially just the free, the bare Hamiltonian, just the simple ramp, right? So just, if I were just ramping the Landau-Zener model, just ramping this two-level system through its avoided crossing without coupling it to any meter or anything like this. This is the original Landau-Zener model that was solved 100 years ago or so. So what you see here is that if I ramp the system too fast, what I'm plotting is the fidelity between the evolved state, the state at the end of the ramp, and the target ground state. So what we want to be is in the ground state of the Hamiltonian at the end of the ramp. If I go super fast, right? So this big T on the order of less than 1, right? You see that the fidelity here is basically 0. So I end up not at all anywhere near the ground state that I want to be in. As I approach the adiabatic limit, we see that I get progressively better and better fidelities. I'm approaching the adiabatic limit. What happens when I introduce this coupling to the meter, I introduce this interaction term that gives rise, that captures essentially this effective dephasing in the energy eigenbasis of the system. What I find is that regardless of what I can pick any time here, any value of fidelity here, and I can always achieve the same performance for some fixed value of the interaction term, right? So for instance, if I take here this fidelity that I get whenever the ramp was on the order of t equal to 9, I'll see all the way along this line, if I couple to the meter with a comparable coupling strength, I can pretty much, you know, get a double, pretty much achieve the same dynamics in about half the time scale, right? And this is essentially, I can always do this, right? I have this sort of lines of constant fidelity all the way along. Now, I think you can be looking at this, and because it's such a simple setting, you can kind of see why this ends up happening. The interaction term here is this, what it in essence affects is a kind of energy rescaling from the original Hamiltonian. So that wasn't exactly necessarily obvious to me from the outset, but we'll see that that's exactly the kind of essence of what it captures. Again, like I stress, like this Landau-Zener model is a little bit of a particularly simplified setting. But again, it just captures the essence of what we're doing. So we haven't talked a little bit yet about what the initial configuration of the meter is. We'll come to that in a second. What I'm showing here in this plot is essentially just the same sort of information that we had here, but just for various different strengths of interactions, right? So what we have in this blue curve here would be the bare Landau-Zener results again. So we have that if I don't couple to the meter whatsoever, what happens is as I perform the ramp progressively slower, I approach the adiabatic limit essentially exponentially. If I couple to the meter with some strength, the stronger I couple it, we see these different curves have varying different, let's say, steeper and steeper gradients, indicating that the stronger I couple to the meter, the quicker I can approach an effective adiabatic dynamics. Now, what we see here is that it's effectively just a rescaling of the time, and that's a kind of consequence of just the simplicity of the model, or at least that's what it sort of appears here. But we'll see that this kind of rescaling is a little bit more general. So we can understand a little bit what this coupling to the meter is actually doing by looking a little bit more carefully at the impact that this coupling to the meter has on the spectrum of the original problem Hamiltonian. So we asked the question of like, what exactly is it that the meter is doing in order to achieve this, in order to facilitate this speed up to adiabaticity. So for simplicity, we've assumed that the meter Hamiltonian is equal to 0, but any Hamiltonian here that commutes with the system Hamiltonian would work just as well. So that's not too important. The more stringent condition was what we initialized the meter in. So what I didn't say in the last slides was that what we assume is that the meter, in order to achieve this really like excellent speed, or like this enhancement to adiabaticity, is that we need to initialize the meter in an eigenstate of this interaction term. So what this interaction term wants to do is to induce a dephasing on the system, which intuitively we would understand that if I can cause dephasing in the energy eigenbasis of the system, I can in effect suppress non-adiabatic transitions. Therefore, I should, in principle, achieve the adiabatic dynamics quicker. The best possible choice I can make for the initial state of the meter is the eigenstate of this interaction term with maximal eigenvalue. That has a surprising, at least I found a surprising consequence on what this interaction term actually physically does. So while the interaction itself appears to be a dephasing type interaction, with this initial state, no actual dephasing occurs. And in fact, the system and the meter are completely uncoupled for the entire dynamics. What it actually does is it essentially induces a rigid energy rescaling to the problem. So if we look at what the spectrum of my original problem Hamiltonian was, which again, in this instance, a simple two-level system, the red curves here are the bare energy states of the Landau-Zener model, right? So it captures that avoided crossing that we have, that whenever the gap reaches its minimum value, I'm very likely to get lots of excitations to be generated if I'm ramping the system too quickly. If I implement this interaction Hamiltonian and I initialize the meter in a state with maximum eigenvalue, what this does is then just pushes the energy levels apart, right? So it does a kind of rigid rescaling of the spectrum of my original Hamiltonian. Now, I think in hindsight, this is kind of clear to see here. And I think for the Landau-Zener model, it seems almost obvious, bordering on perhaps trivial in some sense. But what we'll see in the next slide is that the same effective picture holds regardless of what the details of HS are. So this coupling, in effect, does induce an effective rescaling of the time because it pushes the energy levels apart while sort of maintaining the kind of core spectral features of the original problem Hamiltonian. So I think this is quite nice, and then we can understand why it achieves a speed up to adiabaticity. And it's because, I mean, the adiabatic criterion is such that whatever the minimum energy gaps are, that's what dictates the adiabatic dynamics. Like the size of the energy gaps is directly what dictates how likely I am to see some transitions. By coupling to the meter, I push those energy levels apart, and then I'm guaranteed to do to be able to achieve an effective adiabatic dynamics on a quicker time scale. Now, what we compared to, or what I was sort of interested in understanding, was how does this effect compare to other control techniques, in particular something like these shortcuts to adiabaticity that people have been studying. So the particular details of that are not so important. Just suffice that if I wanted to control this Landau-Zener model using something like one of these shortcuts to adiabaticity, I can work out what the control term needs to look like, and I can see that it also induces energy gaps in the system Hamiltonian. So in particular, this black line is what I end up getting if I calculate something like one of these shortcuts to adiabaticity. And what we see is it also induces a large energy gap where transitions are highly likely to occur, but it does so in a very different way. So this whole plot was essentially just to demonstrate that while this coupling to a meter has a similar flavor to some other control techniques, the physical mechanism with which it achieves the speed up the adiabaticity is somehow fundamentally different. So, and in fact, it's really just to do with a kind of rigid rescaling of the spectrum of the energies. Now, I mentioned that I think I like the Landau-Zener demonstration because it kind of captures all of the essential features of what we're proposing as a meaningful protocol, without getting too bogged down in the details. But somehow the details are obviously important and relevant when we come to more meaningful problems that we're interested in, right? In particular, what about for an actual annealing problem? So we then take the exact same protocol and we apply it to, I guess what I would say, a proper annealing problem. So what we take is our easing interaction, and we take some I think these plots are generated for doing like 100 or 1,000 random instances of these J and H parameters. And we initialize the system in the polarized state. And then what we're going to do is ramp on this interaction term. And the goal is to ensure that the system is always in its ground state. And we want to see if we couple it to a meter using the exact same scheme, but just scaled up for a larger size system, do we see qualitatively the same behavior or exactly the same behavior? And what we find is, again, if we look here along the axes, when it's uncoupled to the meter, we'll get, if we try and ramp the system too fast, we'll generally find that we get we almost immediately will be leaving the ground state, so we don't achieve an adiabatic dynamics. As we go slower and slower, we eventually do approach the adiabatic dynamics. Coupling to the meter then allows us to achieve the same performance, but significantly, in some sense, significantly faster. If I ramp up the interaction strength here, I can achieve effectively the same performance as the instance when there's no meter present, but just much, much faster. And this holds regardless of the same quality of features behave, regardless of the sort of size of the system that we're looking at. And in fact, if you, I think Nicholas went through and calculated everything explicitly, what you'll find is that the reason it achieves the same performance or the same effective behavior is because this coupling term here induces effectively the same rescaling. So there's no coherence that's built up between the meter and the problem Hamiltonian. So our like n qubit easing problem. So no coherence is generated. All it does is it takes that energy spectrum and it just pushes the energy levels rigidly apart. It just induces a shift in the size of the energy gaps. And so you get this kind of linear enhancement or linear approach to adiabaticity quicker. Last point that I just want to mention is, another way in which we can sort of capture the same essence of this, and this allows me to talk a little more generally about the implementability of the protocol, is to consider a slightly different success metric. So instead of calculating something like the ground state fidelity, which is what we have here in the last couple of plots, so really I do the protocol and I want to see if my system stays in its ground state. We can instead calculate another metric called the time to the solution benchmark. So my understanding of this is that it comes from the essence that often these kind of optimization problems are believed to be hard to solve but comparatively easy to verify. So all we want is to ensure that in a given run of the protocol, that the chance in which my system, when I measure my system, it's actually in the ground state is sufficiently high, right? So that's what this P parameter is. As long as that is the case, then I can be, there's a bit of a trade-off between how high I want this probability to be versus how long I would need to run the protocol for. And so there's a slightly complicated way in which we calculate this minimization, but the details of that are not so important. All that is relevant is we can compare how our this quantum non-demolition inspired, this meter coupling protocol works compared to what I called here T coherent. This is essentially where I switch off this coupling term. So comparing to the case when the coupling is 0. So that's what we call like just the coherent protocol. If I look at this ratio between these two, it gives a sort of sense of what the actual speed up is achievable by coupling to the meter. And what we find is that you get this kind of very nice, simple relationship, that you get this like clear linear speed up, a linear approach to adiabaticity, which is, again, a direct consequence of the fact that this coupling with this interaction type of term, this effective dephasing, and by choosing the right initial state for my meter system, I can just induce energy splitting or larger energy gaps in my original problem Hamiltonian. And that's what we plot here. These yellow points, we see that we approach this adiabatic limit, or sorry, we approach this linear, like perfect scale speed up very quickly as for essentially arbitrarily large systems. Now, caveat here, and in fact, what maybe you were sitting thinking is, okay, well, this protocol, though, I mean, what we're doing, especially by letting this coupling term be essentially arbitrarily large, is sort of just washing out some details of what the original Hamiltonian was. So it's kind of clear that we're just doing a kind of effective rescaling of time. This I agree with. What we're interested in, or I think what the motivation here is, that this establishes that it's as a proof of principle. If you can engineer an interaction that's even close to this, it seems intuitive that the one should still be able to achieve an effective adiabatic dynamics maybe slightly quicker. In particular, if we relax the need to get a perfect adiabatic dynamics, in particular something like this time to solution benchmark, just as it captures, we want to see, how close can we get to this optimal performance, even in the case where maybe we relax exactly this form of interaction. And that's what this blue curve is essentially showing. It's kind of like the kind of core final result that we have, which is this interaction term, as I've said, is like very difficult to implement, right? What we have here, if we look at this H of T, involves sigma Zs and the sigma X term. So if I were to try and implement this, what I would need is to couple the meter to all of the qubits in my problem Hamiltonian with a sigma X. I would need a 3-body interaction terms with sigma Zs and these 2-body ZZ terms. What we do is see, well, what happens if we slightly tweak this and we relax that constraint? We don't exactly implement this, but we cut out this ZX interaction term. What that means then is that this interaction no longer perfectly commutes with the original system Hamiltonian. That means there is some energy exchange between the two. There'll be some relaxation, but it's still not a million miles away from the ideal situation that we know effectively works basically perfectly if you can just ramp up this interaction strength. And what we find is with this kind of what we call this constraint protocol is that we still get a modest speed up. That if you can implement this control Hamiltonian sufficiently well or sufficiently close to the ideal, you can still achieve an effective adiabatic or close to an effective adiabatic dynamics comparatively quicker. So again, there'll be a bit of horse trading to do with like something like this time to solution benchmark, but it's kind of proof of principle. This opens up the possibility to use lots of more advanced kind of control techniques or optimization techniques to explore this regime a little bit more. So I think I promised I would talk for about half an hour. I think it's been about 30 minutes at this point. So just to quickly sort of wrap up and just give the sort of high level points. What we did here was just think about, can we use a simple, well-established technique, this quantum non-demolition type measurements to achieve effective adiabatic dynamics on faster timescales. What we find is that, yes, kind of from the intuition that this type of interaction generates an effective dephasing, that's what we thought was why the protocol would work. What it actually turns out that I found more interesting is that it in fact is it doesn't induce any dephasing whatsoever. But what it really does is it just induces this kind of energy shifting. it then opens the door to start thinking, well, what happens if I put some constraints on here? As long as I'm not a million miles away from this type of interaction, it should still work reasonably effectively. So I think I point out that you could read a lot more details about the paper in here. If you allow me just 1 minute for one more very quick thing, it's just to say that we will be organizing myself and Christiana are organizing a workshop in Dresden next July, which is going to be all broadly focused on control techniques. So we're opening it out. The registration and application should open sometime in January or February. So welcome to please apply and consider joining us. And so with that, I thank you all for hanging about. And yeah, I'll happily take any questions or anything like that. So.
Good. Thank you very much, Steve. Lots of interesting things to think about there. And as Steve says, if there are any questions, please either raise your hand or turn your camera on or just speak up or whatever you would like to do. Maybe I'll start with a question. So one of the key things about ground state quantum annealing is you need to initialize in the ground state. I'm wondering with your couplings to, if you add this coupling to the meter, either in the constrained or the quantum non-demolition-like way of doing it, how easy would that be to then initialize in the ground state, which is, in the absence of that coupling to the meter is trivial.
So in principle, it shouldn't make any difference, right? So the kind of interesting or beauty of this approach is that the meter and the system never actually become correlated. So although this coupling term, you instinctively think that they should do, and in fact, in general, if I have like just a dephasing between like a system and an environment, generally dephasing kind of can lead to the global state becoming highly correlated. The choice of initial state for the meter is such that they remain completely decoupled the whole time. So this coupling, in some sense, how I kind of pictured or how Giovanna was explaining it to me, kind of can be viewed as a kind of almost like applying a strong classical field to the whole to the whole problem, and that's why it doesn't change the fundamental spectral features of the system. It just pushes all those energy levels apart. So I think that the initial preparation shouldn't be so much of an issue. The real bottleneck here is actually engineering this interaction, right? I mean, the fact is that it's a time-dependent interaction that is dependent on the energy of the original Hamiltonian, right? Or the Hamiltonian of the problem system, and it's time-dependent. This type of like effective time-dependent dephasing, super difficult to implement, I think, right? Which is, but the hope we have is that from this kind of inspired protocol, or this like constrained is what it was called, and this constrained protocol, that you can still get a modest speed up. You can still do better than the let's say no coupling to a meter. You just pay a little bit. But this, let's say this curve is completely just the simplest case we could imagine. I imagine there's a lot of room for optimization to try and get this blue curve down to what is the absolute best that you can do, which is this yellow curve.
Good to know. Thank you. Any other questions for Steve? If not, let's thank Steve again with a real round of applause from me, half of the audience. And I look that's the end of the seminar today. I guess I look forward to seeing people again next Tuesday's seminar, which will be at 9 a.m. UCT. Thanks, everyone.
Okay, thanks very much, Paul.